All right, so I guess it's about 10 minutes after, but you're probably still going to hold me to 2:30, huh?
No,
we'll give me a little bit extra.
We'll give you your full time.
All right. So otherwise I can speak fast. So anyways, I'm going to talk about challenges for energy efficient scientific computing. Not just the upper crust of the top 500 list. I'm from the National Energy Research Supercomputing Center, which is an LBL computing center here, and we do a lot of open science computing. So anyways, let me start with what's going on in HPC, why there's a power crisis for us. And everybody's already talked about how Moore's law is alive and well. It's this other thing called Dennard scaling that's dead. And Dennard scaling is what gave us these phenomenal improvements in clock frequency as we got our smaller transistors. But the silicon goodness is ended. And if we continue in our business as usual path, which we have actually been continuing on this path straight towards the brick wall, we can't continue this way. And I'm going to talk about this DARPA study that extrapolates these trends. It's interesting that in my conversations with DARPA, they point out that they can't actually make magical technology that we don't already know about in the lab come into existence. If you want something 10 years from now, it has to be demonstrated today. And so the best we could hope to do is find the right things to accelerate in terms of technology to put them into the mainstream. So certainly this is what we're seeing in all of our centers. This is Oak Ridge, one of the DOE centers. And what you'll see here is this is the actual projected, where's that thing?
Top button.
Top button, there it is. This is the projected growth in power for the supercomputing center. Part of it in cooling, part of it in the IT equipment. But we're blowing 31 million of our budget because our budget for power and equipment is the same budget. And it's not that we don't want, HPC isn't actually interested in energy efficiency. We just hate giving all that money to PG&E. And we would probably reinvest that money in buying more equipment. And that gives more capability to our users. So that's really what it's about. And now Oak Ridge, our friends, point out, well, they have cheap power and that somehow solves the problem. Well, actually, if you're large enough, all of you get good power contracts to get cheap power, but you're still given 31 million bucks to your power company. And it's not just about us. It's 2% of the U.S. power consumption. It's a worldwide problem. Google has adopted the same approach, though. Oh, let's locate next to a hydroelectric dam to get cheap power. This is a temporary solution at best. And certainly I understand that Iceland is trying to convince people to go and get some geothermal power from them, but there's only so much ice in Iceland. So, a lot of ice in Iceland. But there's a lot of data centers. So anyways, there's also this recent thing in Baltimore Sun article, 75 megawatts and growing 15 megawatts a year. Baltimore is concerned that they'll run out of power. I gave this talk at another conference, and a guy with his name blacked out in the badge complained about me disclosing this public information. It doesn't matter. We've got 3 different studies, and they all converge to the same thing. We're talking about hundreds of megawatts if we can continue our current approach. In fact, this DARPA study, that's the most recent one, took a really simplistic model based on the ITRS roadmap, and then they also developed a fully scaled model to see what supercomputing power consumption is going to look like in the future. And what you're seeing here are data points from the actual trend lines of real systems that are been fielded over the past decade, and they've been improving in performance with remarkable consistency. But when you extrapolate the trends, even with the best possible technology we could imagine, a simplistic model we kind of turn over in terms of performance at about 200 gigaflops, but with a full model it's even less than that. And this is basically power ultimately limits the performance. So if you think that you need to give more capability to scientists in the future, what this says is scientists will have to live with less if we continue this way. And if you follow that same roadmap, this is what the power trend is going to look like in the future. So we're still talking, even though we're rolled over in performance, about 100 megawatts, blowing 100 megawatts in a system. So demand for supercomputing capability is accelerating. Our users our demands for our services have been growing at an exponential rate and consistently for the past decade. In fact, DOE is even targeting an exaflop system in 2016, and yet the power requirements for this approach are profoundly impractical. So what we need, this is the challenge. Where do you get a 1000x improvement in performance with only a 10x increase in power? And how do you deliver that in 10 years within a finite development budget? And this is not some kind of aggressive goal. This is the usual, trying to sustain the growth rate we've seen for the past 30 years and try to carry it forward another 10 years. This is what we're facing. That is the challenge. So these are kind of the elements, and I'm going to probably blow through this part pretty quickly because I think a lot of the other speakers have talked to these issues in more detail than I can. But you know, this is the areas that we can innovate in terms of performance, and I'm going to touch a little bit in each one. I'm not going to touch on power cooling and facilities because our previous speaker, you just asked Bill Chudy and Dale Sarter, and they've got the goods on that. So first off was the lesson I learned from the Berkeley View. So I started with the Dave Patterson, the Berkeley View, and the very first meeting we had to talk about this, which is now like 4 years ago now. And the key constraints were that you know, power is the ultimate limiter for performance, but we also have issues of yield and design validation. So these are cost-related issues that are tied together with power. So we can't consider power at any, you know, reducing power at any cost. You have to consider the whole ecosystem, how this is all going to work. And I was not on...
You got yield data from a big company.
We got yield... You can talk to Krista about this, but we got yield rumors from somebody who... It's Krista, who was back here yesterday. So,
with a grain of salt.
Yeah, take it with a grain of salt. You know, I got that from Krista. So,
they did disclose that they turned off some of the cores in the natural...
Oh, we actually know that, yeah. And for turning off those 2 cores, even though they were actually there and working, they'll charge you $10,000 for the chip if you have 8 working cores. So they'd sell you the blade. Yeah, it's ridiculous. Anyways, so design validation made the cost unmanageable. I was not on board with this as the solution at the beginning of our 3-year study, but by the end of it, I think all of us kind of converged towards the same solution. You need to go small is beautiful. Simpler CPU cores are more power efficient. Lower clock frequency, you get back some power there. If you take these first 2 approaches, which are good for mitigating the power efficiency issues, you also get to exercise the second 2 approaches, which is you get to add extra redundant processors, like Elad was talking about, to mitigate the chip yield problems, and you get easier to verify solution. And the way this plays out, certainly, you can see it today, is that you know, you drop your clock frequency modestly, and it's not really that you also proportionally reduce your performance, but the V squared term is the thing that you get to drop some, which is the voltage, the supply voltage, and you get this cubic benefit in terms of power. The next thing, if you go to a slower clock rate for the cores, well, you get to use simpler cores, and so that's a whole bunch of fewer transistors, and you get to go with less surface area, which saves on cost, but it also saves on static power loss. And then, so lower leakage, and it reduces cost. And then the last thing is, you heard from Mark Horowitz yesterday, is tailor the design to the application to reduce waste. And this is a tried and true principle for designing iPhones and MP3 players to minimize cost and improve battery life. And just, this is how it plays out. You drop your clock frequency, you know, by half. This is kind of an old slide. You go from 120 watts to 15 watts. You simplify the core, which is what's going on with the Intel Atom. So you go, it's still x86 instruction set, but it's in order, not in simpler pipelines. So you go from like here, a 22-stage pipeline to a 12-stage pipeline to like a 9 or 10-stage pipeline. You get enormous cost savings with a modest decrease in peak performance. And then the last thing is you go with Tensilica, and you can tailor the instruction set architecture to match the problem, and you get a big win out of that too. And you can fit, you can say that, well, each of these cores are less computationally efficient, but damn, you can fit 400 of them on a chip, and it'll still consume less power than the original server design. I don't want to disparage Power 5 servers. The reason that they use that design is most of that surface area is used to hide latency so you can get maximum serial performance. But the point here is that if you have parallelism in your workload, then my gosh, you better go to these simpler cores. Instead of emphasizing serial performance, emphasize throughput. So in the past decade of HPC, optimization target is minimize the price at all costs. So you can jam more equipment into a room and have a whole lot more flops than everybody else in the universe. And that's not just peak flops in the top 500 list. It actually ended up being delivered flops on real scientific applications. You just couldn't beat the COTS approach. And this leveraged Moore's law density improvements. But our next decade is minimizing power consumed for the work performed. That changes our design point, and now, whereas we're opposite, completely unaligned with the embedded space, we wanted power, performance at any cost, we're really design limited by power, and that puts us in line with the embedded space, and that changes everything, and it puts us on a Bell's law curve, where instead of doubling the number of transistors in chip, you think more in terms of cost efficiency. I'll talk more about this commodity, not COTS, but we have this interim solution of accelerators. All I think of accelerators as doing, though, is proving that this approach of massive parallelism with lots of simpler cores is, in fact, the correct approach in terms of delivering more performance per silicon area than the mainstream approaches that we're using right now. So, I think that embedded in consumer electronics kind of design approaches are in our future in HPC. And this convergence is inevitable because it minimizes both cost and power efficiency, and those are the two most important things for us moving into the future. So, let me see, how much time have I blown? All right, I've blown quite a bit of time, so I'm just going to comment quickly on the on power efficiency here. One key thing to point out is that we have traditionally, with parallel machines, depended on fully connected networks, kind of fat tree topologies for the interconnect designs. We cannot continue on this approach because as we scale up our machines, we get these ridiculous exponential curve that we're on, and it's not sustainable into the future. We need to go to a lower degree interconnects, but the question is, do those scale? If the performance of that approach does not scale into the future, then you're just wasting performance in order to save power, and that's a zero-sum game. So we actually looked at a whole bunch of different applications. We found that, in fact, most scientific applications have very sparse communication patterns. Unfortunately, you say, oh, well, then we should just use two-dimensional meshes. Well, the problem is that these patterns are not isomorphic to a two-dimensional mesh or a hypercube or any of these things that vendors have pitched in terms of interconnect topologies. So although it is a low degree of communication topology here, it doesn't really map to fixed topologies. So what we've done a lot of research on is using optical circuit switches in order to kind of map out these switch components so that we could have a more scalable design. So we go, this is your fat tree network topology, or really a close network, and you could actually get away with a whole lot fewer switches if you use optical circuit switch to dynamically rewire this kind of thing and map to the topology of the application. And the great thing about optical circuit switches, they consume a whole lot less power than the packet switches, and that's a great opportunity for improving power efficiency of interconnect designs. Even if you move on chip, we've been working with Karen Bergman at Columbia State University, and this is the photonic on-chip version of circuit switching. These photonic ring resonators allow you to switch things. Unfortunately, they don't understand packet boundaries, so you have to be very careful where we use them. So what we're seeing by using these optical circuit switches on chip and experimenting with different interconnect topologies and replaying real application design patterns, because a lot of the stuff was designed using these random test patterns and crazy stuff like that, then we really can achieve a 27 times improvement over a pure electronic solution. However, it can't be electronics alone. We still have to use an electronic solution to deal with the small message flows, but for large bulk flows, which appear a lot in our apps, it's very useful. Memory had been a small fraction, but this part of the pie is actually growing at a shocking rate as we go into the future. First off, the cost of memory technology has not been scaling as well as the cost of flops that you can jam onto a chip. And the memory density is also not improving as well. But the worst thing that's killing us is this is a picture of a DDR3 memory chip architecture. And the thing that's killing us is that we have this overfetch problem. This is our memory array here. And whenever you ask for just one word of data, you end up getting 8 kilobytes worth of data actually gets latched in. And this is a huge source of power loss in the chip designs. And it's only getting worse because as we go into the future. So we extrapolate out to that exaflop scale system that I was talking about. 590 megawatts of power would have to go into the memory subsystem if you extrapolate these trends out. And most of that is due to that overfetch problem that I was pointing out. However, the guy who gave me this slide, Dean Klein from Micron, pointed out they're also losing $1.5 billion per year, so don't be counting on them to fix this problem tomorrow. This requires a major reorganization of DRAM to fix the overfetch problem, and also the interface is another place where you're losing a lot of problems, so maybe optical memory interfaces and chip stacking, but that's only half the problem. You really got to fix the internal architecture of the DRAM too, or you don't have a solution. And what we have to live with is less memory and less bandwidth. Algorithms, well, this is what users of our supercomputing systems are seeing. This is the actual average increase in concurrency for the largest scale supercomputing systems, and it's going to continue up that way into the future. And everybody's scared shitless, to say the least. So what do you have to do? We need to reformulate our algorithms to actually, to first order, change our discretization for, this is an example from the climate code. Right now the discretization is this thing that has a singularity kind of at the North Pole, and this is totally impossible to deal with if you have a billion-way parallelism. So we have new discretizations like this soccer ball discretization or the cube sphere from NOAA. And so we have to rewrite our algorithms and our core codes to exploit parallelism, and that's a lot of re-architecting of code. But another thing to point out, though, is that we're counting on the hardware people to deliver just a total of 3 orders of magnitude in terms of performance, but our scientists need 12 orders of magnitude, and they need it in 10 years in order to field their next big science experiment, this $12 billion ITER system. Now, first off, we're not getting improved clock processor performance or efficiency, so that's out. So what does this say? This puts the hardware guys in their place. We aren't going to get them what they need. The real question is, how do you change the hardware design to make these 9 orders of magnitude easier and more accessible to get? And when it comes to hardware architecture, we've been in this mode of, what do you do? What are the architectural features to improve clock frequency? It's all bull. What you need is to focus on what are the hardware architectural features that directly map to real algorithms that will be used to get scalable performance into the future. For example, fast global reductions for implicit solvers, or adaptive gridding, you need hardware support for load balancing. These are the things that you need in hardware architecture in the future, and we're completely upside down in terms of that. So the real consequences of this is we have to find strong scaling. What strong scaling is same size problem, but increased performance by adding processors. And it's a tall order because all throughout the 1980s, this was used to argue against MPPs. This is a stupid idea because you can't get strong scaling, and there's lots of proofs that you can't get strong scaling. So you should be afraid, very, very afraid, if you're an algorithm designer. Software performance, don't have a human do what's a machine's job. Everybody talks about memory bandwidth and flops like it's the only important thing. Well, we look at all these codes. Red is the flops, blue is the memory bandwidth contention. Most of the time is spent in other, and other is latency stalls. And we need to figure out how to recoup other, because we shouldn't be having latency stalls, particularly in scientific codes where you know exactly what the address stream should look like for all time. So it's ridiculous that we have this big other category, so big. It means compilers suck, basically. Is there a compiler architect here? Sorry. So what we do is, and so it's also resulting in non-portable code. What we're really doing here with auto-tuning is taking all the tricks and tips that we've accumulated over the years on how to optimize code, and we have the auto-tuner actually manually tries out all the possible combinations of tricks and tries to find, this is 600 different loops and this is performance of the vertical axis, tries to find the combination of tricks that works best. And what you get is you go from having flat performance for multi-core, we can recoup back 3.5 times to 7, even 10 times performance. And so code optimization is a huge opportunity for improving power efficiency. Forget the hardware. Make the code run faster. That's 10x power efficiency improvement right off the bat. That's great. So auto tuners and languages, and I'm not going to go into this because I'm running out of time. So how can we achieve our goals cost effectively? This is still an important problem because this is where I'm at. You know, I'm at a big supercomputing center, but this is where the money's at. It's down here. So if we can't figure out how to make something that's useful down here that we can exploit up here, then we can't afford the $15 billion NRE that it costs to make the solution, because we only got $2.5 billion in hand, and that's across all the supercomputing centers. So, you know, how do you maximally leverage the bottom of that pyramid? Because we're really hangers-on. Something I had learned recently, this is from Sugio Makimoto, this is Japan. You know, the PC industry's actually been pretty flat there. The thing that's taken off is the consumer electronics stuff, which is kind of interesting. So 2010 and beyond, R&D investments in future technology are all going to that consumer electronics. Moreover, if you look at units sold and revenue, embedded has always been more units sold than the desktop stuff, but gosh, we made a ton of money on the desktop stuff. And what happened here is it got flat, and IBM saw this, and their reaction was, sell off the PC unit, quick, quick. And so they sold off to Lenovo. Apple saw this trend, and they introduced a consumer electronics device, and within a short period of time, it ends up being 50% of their net profit. So I said, well, that works pretty well. Let's do an iPhone. So this is where all of the resource investment in the future is. I'll also point out that the Intel Atom, which is an embedded version of the x86, is now the engine for the fastest growing portion of the laptop market. So the embedded guys have developed an amazingly lithe tool stream. This is from our friends at Tensilica, where you can actually tailor the chip design for a 9-month turnaround, and it actually, once you tailor the instruction set, it'll pop out not just the Verilog, but all your software components too that you need. And this is designed for, they could create 200 new designs per year, and this is very different than what we're used to. In fact, the entire embedded space is much, much more responsive to design trends and tailoring the design to achieve power efficiency. So I kind of see this continuum here that we need to exploit in the HPC space, where we have an ultra-efficient chip multiprocessor to drive our smartphone stuff. But then if you add to it like a whole bunch of external I/O bandwidth, well, gosh, you got a pretty good chip for data centers that leverages a lot of the technology from down in this end. If we add floating point and some fault resilience, then we actually have an excellent chip for supercomputing applications that leverages a lot of stuff from the data center space. And so this seems to be a compelling, way to have a scalable ecosystem as we go into the future. So if this is such a great idea, then why don't you do it? And this is Microsoft. I have Microsoft to thank for the term dog fooding. It's now in the dictionary for, if you think it's such a great idea, eat your own dog food. Use your own design tools, because all of our developers complain about it, so we'll make ourselves use it. Uh-oh, I'm out of time. So I have 2 minutes? All right, I'll get through this quick then. So our overview is, this is research, it's not a product. Elements are, we start with the application target first. Usually in HPC, we buy a bunch of machines, we jam them into a room, and then we try to figure out what runs on it. Well, instead, we do like the embedded guys. Choose the science first, design the system around the needs of the science, and design the hardware, software, algorithms, and hardware all together in a tightly coupled loop. What's new? Well, everybody said, oh, everybody's done custom design before. What's new about you guys? Well, we're leveraging a commodity process for designing power-efficient embedded chips. And this thing is an engine. I mean, it really works. We're just redirecting it for scientific computing. And we're using auto-tuning to do the algorithm mapping, and we're using RAMP, which is a chip emulator, to accelerate our design approach. And so climate, this is the current resolution of the climate model. As you can see, the Bay Area not very well resolved. We want to get over to here. That's at least 1,000 times improvement in performance, but it does another thing if you get over here. It's not just that more resolution is better. You can't model clouds if you're over here. Here, the patches are small enough that you can actually do direct modeling of clouds, and that's a transformational change in the science, because everybody agrees that the statistical models for clouds, when you have these big patches, are just complete rubbish. And to get better models, we have to get to a machine that supports this resolution. We did a detailed design study of this, and we found that it's about an exaflop scale problem. It would require about 20 million or so processors to achieve that. As I said, we're taking that tool chain, we're repurposing it to deliver a power efficient chip for scientific computing. We had a straw man design. This is a little thing we put together with Chris Rowan, but the straw man's not good enough. The straw man, this creates an unfair comparison between other chips, but we think we can do in 3 megawatts what, off the shelf system, and this is 65 nanometer technology, would require about 180 megawatts. So we tried to do this in a more detailed design study. Mark said yesterday, years of research in embedded computing showed that there's only one design technique that works, it's reduce waste. Seymour Cray said the same thing about 20 years ago. And we wanted to try this out. So first thing is that our common desktop chips that we use for commodity stuff have this accretion of functionality, and they add all sorts of things that we don't need over time, and it consumes power. With these DSP, these embedded chips and the Tensilica tools, we can actually design a chip around our application, and it has a whole lot less crud on it that we don't need. And in fact, this is a short list of instructions in the x86, which is our primary supercomputing chip that I don't need, and here's some more, and here's some more. It's a lot of instructions that I don't need. Out of 300 assembly codes, we only use 80 when we compile our supercomputing codes. And it still has like stuff from the 8087 and 8088, SIMD, there's all sorts of stuff. 32-bit instructions, 16-bit instructions. It's amazing what's in there. You chop all that off, we get an 80x improvement right off the bat. So go from a Core 2 to an Atom to a science-optimized design with double precision arithmetic. We can add features that are directly mapped to our programming languages that we use for science applications, and it reduces the amount of redundant data transfers that happen with cache coherence. We've experimented with different on-chip topologies. If you have 100 cores in a chip, it's kind of a problem to intercommunicate. We're as fault tolerant, if not more, than a conventional design. People say, oh, you're going to have 1 billion processors. The failure rate will be astronomical. No, we're exposing less surface area, okay, than anybody else. And I'm out of time, so I'm just going to skip the last set of slides and have my conclusion. All right, come on. So, summary. I think that we need to change our notion of commodity. It's what's on the chip, commodity IP arranged on a chip, which is what we learned from the embedded space. And our approach is to choose the science target first and design the machine around the problem, and we do it cost effectively. And it's ultimately, whether we do it or somebody else does it, it's where HPC is going to go. It just has to.
Wow, okay.
All right.
Yes, please.
Yep.
So, as we learned under the DARPA HPCS program, where P stands for productivity, the problem with your approach is that if you tailor the machine to the application, it's not portable. And 3 years it'll be rendered on the next machine. You'll have to do an incredible amount of work to port it. Secondly, that you can't use all the standard tools to port it. Your software programmers will have to do an incredible amount of work at low levels, so that you'll have a great exascale machine that will be running this application that nobody can possibly verify and validate. So I'm curious as to how all that will play out.
All right. So I guess I went through the second half of my presentation too quickly. First off, everybody, including the manager of the HPCS program, laughs whenever somebody says productivity. Second, those machines, the design constraint for them was performance at any cost, including power and actual dollar cost, and I told you that those were the two things that we need to optimize. So HPCS went completely and entirely off the rails as far as that was concerned. Thirdly, we are using a fully programmable solution. In fact, we're very pedestrian when it comes to, with the embedded tools chain. We can actually design things around a consistent programming model that's reusable across multiple codes. In fact, we're designing around the PGAS programming model from UPC. The HPCS folks chose to depart from that and do something crazy, and they got what they paid for. So I think the lesson to learn from the embedded design space is if you that you have a lot more opportunity to tailor when I say tailoring the machine architecture of the problem, I'm saying you can tailor the speeds and feeds and the sizes of the caches, and all of those things are transparent to the programming model. So I'm not, you're basically mistaking the old approach of full custom design, where you actually have the logic is tailored to the problem, and that's directly exposed to you through the programming model. That's not what I'm saying. I'm saying that the embedded space, we can, tailor the instruction set, we can tailor the sizes of caches, and those aren't exposed to you in the machine model.
Okay, maybe one more.
Yep.
Hey, thanks for the presentation. So you mentioned the Dave Patterson view on parallel computing
Yeah,
thing.
it was about a dozen of us that met on a weekly basis for 3 years, but yeah.
Right.
Dave started it.
So there seems to be a contrast between high performance or scientific computing and, say, more web-oriented computing.
More what-oriented?
Web-oriented,
Web-oriented.
internet-oriented computing like Google, Yahoo, Microsoft type data centers. In your opinion, what is the fundamental differences between, say, scientific problems and web, internet business problems that makes perhaps the design points in HPC and Google, Yahoo data centers different, and whether that will result in fundamental differences in the solutions in terms of power efficiency?
Okay, so I don't think it'll result in fundamental differences, and that's why I gave you that continuity diagram. I do think that we could reuse a lot of the guts of the chip multiprocessor design across all of these spaces. Now, the things that make a cloud, let's say, unsuitable for HPC and would change the design point are that a lot of our algorithms are highly synchronous, and a lot of people think it has to change, but it's the best thing we got going right now. So we're very latency and jitter sensitive in terms of the algorithm design. So that means that you have to emphasize low latency in the interconnect rather than high throughput, which is what the data centers do. But most of the optical drivers and the protocols could be reused. It's just the way that you wire it up, so the point-to-point connections that would be different than what you have in a data center. The second thing is we care about floating point. We still do care about floating point. The data centers can survive really crummy floating point units. The third thing is that the reliability and fault resilience is more important to us. In a data center and web application, all of the important application state resides in the client side, not in the server side. And in our case, that's just not the case. It's too much data to be moving around. So because of that, we have to have more sophisticated fault resilience mechanisms than would work in a data center. But other than that, I still think there's the opportunity for 90% reuse. It's just that you can't use EC2.